Okay, so this is my Game Physics 2005 Assignment 3 and 4 combined for Angry Birds. Let's just jump right into it. So we have our Angry Birds script to start. We start this script by declaring some variables used to set up the physics of the projectile and some game objects for the launcher and sphere prefabs. In our update function, we get the mouse position on the screen and convert it to world space, storing it as a vector3 called mouse position. Then we begin working on our slingshot that Connor showed us how to make in lecture and draw a line from our launch to our mouse. Upon clicking the mouse button, we instantiate our sphere prefab and set it to the launcher's position and fire the sphere based on the slingshot vector and our multiplier of 10. Here I attempted to switch prefabs to simulate switching birds, but I was unsuccessful. It just made my game glitchy, so I decided to leave it out. In our fixed update, we are applying gravity acceleration to our sphere's velocity and then drawing a debug line to represent this. Moving on. Our physics object script. We set up several variables with ranges such as mass, which we prevent from being zero to avoid trying to divide by zero in a later calculation. Drag grippiness, gravity scale, velocity, net force. In our start function, we get the physics shape component attached to this object, and we store it as a shape. And then we add this object to the physics engine list of objects. In our physics shape script, we define our shapes in an enum and create an abstract function called getShape to be overridden later. For our physics shape cube, physics shape cube, physics shape plane, and physics shape sphere. These were all relatively similar in their scripts. I'll just show you here. In that they all got their respective shape and found their normals. The exception was the cube script that would also return the half extents by taking the local scale and dividing it by 2. So we use that function later in our physics engine. Okay, so right into the meat and potatoes of this script here. This is our main script for this game. We start this script with a struct so that we can return both a bool and a vector3 for later use. Then we added a singleton so that there can only be one instance of our physics engine script. Then we added a list of objects to be added to later, and we define our delta time and gravity acceleration. Next, we have a function that returns gravity force, which is our gravity acceleration times object's gravity scale times object's mass. All right, so our kinematic update here. Oh, good, I can show it all on the screen. Inside our kinematic update is where we update our objects with our kinematic equations. We do this by iterating through each object in objects and add gravity to our net force of object A. We created a bool called isStatic to disallow certain objects from moving. If it's not applied, we begin calculating our acceleration by dividing net force by mass. This is where the prevention of zero mass comes into play because we don't want to divide it by 0 and break the world. Then we calculated our drag force using our drag coefficient and velocity squared. We added this drag force to our acceleration and then updated velocity based on acceleration. Once we updated the new position, we were free to draw lines to represent velocity and gravity. So our collision, actually, I'm just going to make this smaller. Oh, I still can't fit it all. That's fine. Okay, so we used our collision update to check for and handle collisions between all objects. This included sphere to sphere, sphere to plane, plane to sphere, sphere to cube, cube to plane, and cube to cube. While most of these calculations were from our labs and served as a reference point, sphere to cube, cube to plane, and cube to cube was written by me, and they use new functions that I'll get into a little bit later. But the majority of this was written in our labs. Yeah. So in our labs, we created an if statement block that would check to see if collisions occurred between two objects. If it did, we would change both objects red. It would also calculate gravity. Hold on a sec, I'm not even on the right page here. There we go. Okay. If it did occur, it would change both objects to red. It would also calculate gravity and the gravity dot normal, which was the dot product of the gravity force and the collision normal. Our gravity projected normal would scale the collision normal by the dot product to get the gravity forces component along the normal. We then calculated our normal force, which was the opposition of our gravity projected normal, which is why it is in negative. Right here. Okay, then we colored it green and applied the normal force to both objects in opposite directions. Then we calculated the relative velocity of object A with respect to object B, and we used this for our collision info.normal to calculate our velocity normal. We would then use this and our collision info.normal to calculate our velocity projected normal, which is the velocity component along the normal. Then we subtracted the normal component of velocity from the relative velocity, leaving us with only the velocity component parallel to the surface. If that value was greater than a small number above 0, right here, well, it says due friction, was the comment we made in the lab. The coefficient of friction was determined by the object A's grippiness times object B grippiness. We then calculated the friction magnitude from there. The friction force, which we learned acts in the opposite direction to the velocity on the plane. Visualizing this in orange draw lines, we then applied friction to both objects in opposite directions. Okay, so our collide with spheres checks for collision between two spheres. It does this by calculating the distance between the centers of each sphere and calculating the overlap, which is the sum of their radii minus the distance between their centers. If the overlap was greater than 0, they are colliding. If they're colliding, we calculated the minimum translation vector to separate the two spheres from one another in opposite directions. Moving on to our collide with plane. Our collide with plane function works similarly. We calculate the vector from the plane's position to the sphere's center. Then we calculate the distance of the sphere's center along the plane's normal. If the plane is also a half space, we used extra steps to ensure that the sphere stayed on the correct side of the half space. But if it's just a regular plane, we calculate the overlap between the sphere and the plane. Then we determine the collision normal. We calculate the MTV and move the spheres slightly to resolve the overlap. Sorry, I'm speaking quickly because I don't know how much time I've already gone through here. Okay, so in my collide with cube, we manage collisions between the sphere and the cube. First, I got the center position of my sphere, my cube, and the half extents of my cube, which is just the half, it's just the half the side lengths along each axis. So you can see that in here. Then I found the closest point on the cube surface to the sphere's center. This was done by clamping the sphere's center coordinates to the cube's bounds along each axis. Then I calculate the displacement from the closest point on the cube to the sphere's center. And then calculate the distance squared so I don't need to square it later. Then I move on to checking for a collision. If the squared distance is less than the square of the sphere's radii, a collision has occurred. If that's the case, I move on to calculating the normal and the overlap into the cube. Using this overlap, I can calculate how much MTV is needed to move the sphere out of the cube. Then I adjust both the sphere and the cube's position by moving both along half of the MTV. Okay, this is my collide with plane 2 script. It was much of the same logic, except it's determining collisions between cubes and the plane and or half space. I still calculate the overlap in the same manner as my collide with cube, except instead of applying half of the MTV to both, I only apply it to the cube as I didn't want my plane to move. My last function here is my collide with cube 2. I used it to check for collisions between cube 1 and cube 2, which was essential for getting the structure to stack. The first time I tried this, I didn't have this function, and the entire structure would just sink into one another. So first I calculated the center positions and the half extents of each cube. Then I calculated the displacement vector from cube 1 to cube 2. Using this, I was able to calculate the overlap on each axis by adding the sum of half the extents minus the absolute separation along that axis. If there was no overlap on any axis, nothing was colliding, and it returned false vector 3.0. This if statement right here, this if statement was used to determine which axis had the smallest overlap so that the collision normal would be properly calculated. Then the MTV was calculated and both cubes were moved to resolve the collision. And if we take a look at what that looks like in game, so I'm not really sure why it sinks and then it stops, but it looks like it kind of just settles the gap between the objects. But as you can see, my sphere to cube collision works, my cube to plane collision works, if I can hit the other one, my sphere to sphere collision works, and the whole thing topples down. And that's all I had. Great, thanks for watching.